And from the table, that means that my t-value is going to be equal to, is it 117.6? 117.6 minus 88, holy big difference, 0.1. And then the difference between the two should have been 0, so that second parentheses is 0. That's what I was talking about before. Our assumption in our null hypothesis is there is no difference between bounty and the generic, so that's why there's a 0 there. This difference between the means of the populations should be nothing. And then down below, again, this is coming from the table. And from the table, that's 6.64. No, 6.64, sorry, squared over our sample of 30 plus 6.30 squared over 30. And the t-value that I get, based on my information here, is 17.64. And don't forget, you need your degrees of freedom. The good news is both samples are exactly the same size, so it doesn't really matter. And it's 29, but if they were different, remember you take the smaller one and find the degrees of freedom. And what this is talking about is that you want to have your p-value. So your p-value that you're going to use is the probability that your t, holy moly, is greater than 17.64. And when you do this on your calculator, you would do TCDF of 17.64, comma 99, but don't forget you have to put in your degrees of freedom of 29. And the answer that you get is, holy cow, 17.64. It's got to be 0. Okay, so that's so far beyond. Like normally when we talk about 99% confidence interval, we're talking about 2 point something. So if you're at 17, I mean, that's ridiculous. There's nothing. It's not going to happen. Bless you. So in your conclusion, what you would say is, our result, and sometimes I like to write down this, you might have seen this before, or one more extreme. That means that would be even farther away. I don't know that you need to put that in there. Of p equal to 0 roughly would occur if there were no difference in the means. Since our p-value of 0 is less than an alpha equal to 0.05, we reject the null hypothesis. We have, I would say, convincing evidence that bounty towels are stronger than the generic ones. Okay, so in this last one, as we talk about it, what you'll notice here is that we have a table instead. Aaron, shut up. That's the first time I told you to shut up. And this one, we're doing the same thing again, except now we have to do something with the data. Notice how there's only 5 pieces of data. So central limit theorem doesn't apply, draw a picture. This time, because they both look like they go within a certain range, I'm going to try and stack the dot plots. So my H0 in my statement, after you read this stuff, is that my two means are different. What do you want to call the first one? Mu1 for group 1?
Sure.
All right. So I'm going to say that my null hypothesis is mu1 minus mu2 doesn't change. And for my alternative, I'm going to say that the difference between mu1 minus mu2, what was the claim? More in 2 weeks. So it's going to be greater than 0. Because they're saying that in the 2-week one, which was mu1, was more than this one, so that's going to be greater than 0. If you did them the other way around, you'd have to say less than 0. So mu1 is the mean breaking strength of polyester after 2 weeks. And mu2, which is not a Pokemon character, is the mean breaking strength of polyester after 16 weeks. I'm pretty sure that 16 weeks is going to be weaker. Just a guess, though. In our planning stage, we will do a 2-sample t test for mu1 minus mu2. Yeah. I don't know if you guys get to the same point, but there's a certain point where I don't even look up anymore. I just say things like, we have 2 simple random samples of polyester breaking strength, blah, blah, blah. Okay, so like I told you before, if we don't have this stuff, we can't do the test, so might as well say it. We have 2 sets of random breaking strengths of polyester. Oh yeah. Before I do the normal, I think I'm going to do the independence thing. Did they say they were independent? No? Okay, that sucks, but whatever. I'm just going to go with this. We assume the one set of breaking strength does not impact the other. So the samples are independent. Again, if you can't say these 4 conditions, we can't do anything mathematically. So if they don't give you enough information to say it, then we say it anyways. Just say it anyways. What the heck? Since the samples are less than 30, we will do a dot plot. So this time when we do our dot plots, let's put them together. So in the dot plot, we go from 1, oh no we don't, 98. Oh my goodness. So here's 100, and the highest one is 140. Does that look right? 140, 120, 110, and 130. And let's do group 1 first. So I have 118. This is group 1. And then I have 120. And then I have 126, 126, and 129. Oh, that's pretty tight. Does it say 119 on yours? Okay, that's weird because mine says 129. Can you change yours, please? Yeah. Thank you. 129, in case you don't have that. I'm sorry, I don't know why it's 119. No. Weird. Okay, then for group 2, I'm going to change color. And in group 2, I have 124 and 98. 110 twice and 140. So the orange to me looks a little bit skewed right, doesn't it? Maybe slightly skewed right. And the blue looks pretty normal. So I'm going to say, I guess, what was the first one? The first one was group 1. So group 1 looks approximately normal, and group 2 looks slightly skewed right with no outliers really. So normal. I don't want to write it all down, you guys. I mean, we're crunched for time. I got like 4 minutes left. Our t. We're finding our t value. Again, our t formula in this case is going to be x1 bar minus x2 bar minus mu1 minus mu2. Again, we know that that difference is supposed to be 0, so that second parentheses should always be 0. And then we have the square root of s1 squared over n1 plus s2 squared over n2. When we do the math from our stuff, we find out that these numbers turn out to be, I get 123.8 minus 116.4. Again, this comes from your one variable statistics, minus 0. You guys can check my math on that. And then down below, I get 4.6 squared over 5 for the sample size, plus for the second one, 16.09 squared, all over 5 again. And when I get done, this turns out to be 0.989. Don't forget about your degrees of freedom. Your degrees of freedom here is going to be 5. So I probably should write that down somewhere, degrees of freedom. 4, thank you, because the sample was 5, thank you. So when I look for my p-value, my p-value is talking about the probability that my t is bigger than 0.989. And I get that that value is 0.1893. And again, you can do this doing the T, C, D, F of 0.989, comma 99, comma 4. And that's how I got that p-value. And your conclusion, of course, is going to be that our results would occur 18.93% of the time if the true difference between the breaking strengths was nothing. Since our p-value of 0.1893 is more than our alpha of 0.05, we fail to reject the null hypothesis. That is that we don't have enough evidence to say that there is a difference between the breaking strengths.